Okay, so this video is the stats primer. It's also kind of the overview because it's going to cover a lot of topics that you could potentially come across in the process of reading research, either in this class, in another class, in graduate school, or in life. If someone were to make a wild claim that you want to know more about, you could go into Google Scholar, look it up, and try to read those, right? So this is a skill for the ages, as it were. This particular video will cover about the first half of it, maybe a little bit more than half, are things that we're going to cover to some degree in class. And the second half slash last third are not. Now, there's a couple purposes for this. One, I think it's very possible you might need 2 passes on some of this stuff. A lot of it should build on what you saw in stats class, but my experience is that students' experiences in stats class varies widely. Um, so so you might need a little bit more to truly understand some of these concepts. So one thing I'm going to do is go over those concepts here. And in case your article or another article in another class or an article in grad school or an article in life when you want to learn something because someone's made a wild claim, there are other models that are more complex featured at the end of this video. To that end, I've put slide numbers into all of these, which I try to do generally, but specifically, this outline will tell you where to find the topics that interest you in this particular video, because it will be long. Sitting here thinking about what I'm going to talk about, it will be long. So that you can target it later and come back to it and just not just, fall off the horse mid watching it simply due to length, right? So you should watch this in a targeted way, okay? The topics here, normality, this review relates very closely to what you're doing pretty much immediately in the labs. It's going to build a bit upon things we are doing in class already. The second one has to do with group differences and the famous p-value that goes with that. Other relationships such as correlations come after that, and then I talk a little bit about the difference between repeated measures or paired samples, just kind of conceptually. And all of those things will show up in class. Now, the things down here in the bottom, specifically multivariate ANOVAs and fancy stuff, are things that might show up in a reading or your reading or whatever that we will not talk about in our classroom. But here you have access to that information if you need it for any purposes. Additionally, slide 19, you'll see says applications to NHL project. We will do this slide in class, but you are welcome to look at it here as well if you didn't get it in class or want to review it or whatever. Okay, so normality, which hopefully in your life you've looked at several times. Normality has to do with a distribution, right? Like a bell curve. And so if I ask the question, what is skewness, what is kurtosis, we are talking about bell curves, okay? Now I want to start with this. Now if you'll see here in my definition, skewness means that the data in a curve are clustered to one side or other of the mode, okay? And I want you to look at these two curves, okay? Now to orient you, the curve itself is red, then it has the mean, the median, and the mode. And we're going to talk a lot about the mode right now in skewness and kurtosis because the mode is the most frequent value in a frequency distribution. A distribution in the sense that we're talking about right now has to do with frequency. How frequent are particular values represented in the population that you're studying, right? So here, if I want to look at my negative skewed curve, let's imagine for just a second that this has to do with average, I don't know, ticket prices to the fair. Let's just pick something absolutely bizarrely random and unrelated to anything we're talking about, just for the sake of argument. Average ticket prices to the fair. And on the left, this first curve we're seeing, let's imagine that this is ticket prices, this is the whole year. And the question is, some of those points represent ticket prices in July when people love to go to the fair, and some of them represent ticket prices when there are sales, right? That there are, like it's December, we don't think you're going to come, so we're going to make it cheaper or whatever, right? So let's imagine that's what we're looking at here with the left skewed, right? So the most frequent ticket price, hypothetically, let's say it's the blue vertical line, the mode. Let's say it's 15 bucks a person, let's say. And then throughout the year, for various reasons, sales or specials or whatever, there are other ticket prices that fall under this curve. And, there's some that are way down here in the skinny part where the red line's really close to the x-axis, the horizontal axis, right? And so it just so happens, let's say, that in this first curve, that the ticket prices are left skewed. Now, what does this mean conceptually? What this means conceptually is actually the second thing down here, because I didn't design this slide in a very cohesive way. But negative skew, which is to say your skew statistic is less than 0. So if you were to calculate it, the null number pop up would be negative. Okay. What it means is more of your data, more of the instances of ticket prices is below or to the left of the mode than it is above, right? Now, when I say negative skew, you can kind of assess this visually as well. If you don't have the statistic, you take your fist. I'm putting it like you or me, right? Anyway, like you're looking at me. In a classroom, I'd be turning around, holding my hand up to the board. But it should look like this, right? You should be able to hold your fist up, and your little thumb should be sticking off to one side. And if to fit the data, right, and you can see it gets skinnier on the left in this picture. To fit the data, you have to stick your thumb out to the skinny part. That's skewed and left skewed. Notice that my thumb is pointing to the left, okay? Negative skew and left skew is the same thing, basically. The negative is a little bit more of a technical way of thinking about it because of the skew statistic is a number. But left skewed or negative skewed, right? My little thumb has to point out to left. The opposite is true in a positive skew or right skewed situation. Now let's imagine, now this one is tickets to Disney World, right? Which are always expensive, but once in a while they're very expensive because it's Christmas or it's the Halloween thing or whatever. People love to go to Disney World would know these things better than I. And so now there's the average price is the mode. Let's say the daily price to go to Disney is, let's say it's $100. It's probably more than that. Well, let's say it's $100. And then there are certain days of the year it goes up to 300 or whatever, right? And so in order to find that, first of all, you're looking at there's lots of instances where it's higher than the most average price, the most frequent price, the mode, right? So most of the time it's 100, but there's lots of instances where it's more than that and very few when it's below, right? Now, again, we can use our thumb trick. I can stick my thumb up again. I'd be holding it towards the board, and my back would be facing you in a normal classroom. But if you hold your thumb up, your little thumb, if it fits into the skinny tail on the right, that's right skewed or positive skewed, right? And as you can see in my definition, your skew statistic will be positive and greater than 0, and more of your data is above or to the right than it is below the mode, okay? This helps us visualize what is going on in these curves, right? And this is a very easy way to kind of get a sense of what's probably under the hood, under the curve, right? Now, skewness has to do with stretching one way or the other. Then we have kurtosis, right? And what this means is how tightly is the data clustered around the mode, okay? Once again, I'm going to show you these curves. And now I have a normal curve under A. So I have a normal curve under A, so-called leptokurtic curve in B, and a so-called platykurtic curve in C. And if I accidentally call it kurtotic, apologies. I called it that for many years before I learned the adjective is kurtic, and occasionally escapes my mouth because I feel like osis should turn to otic, and I'm pretty sure other people have said it that way to me too. It's fine, whatever. But this is the technical term. If you study statistics, people do study statistics. All right, so mesokurtic is a nice, lovely, equal curve. This has to do with standard deviation, which is to say the proportion of, it has to do with the percentage of the data that fall within a certain band around the mean or the mode in this case. And we have an assumption that a so-called normal curve, I think it's something like 68% falls between one standard deviation above and one below, right? And then a certain percentage falls past that. So it's this nice curve, and what was kind of this perfect accepted amount is on either side. But sometimes it's really, the values are really close to the mean, and the mode again in this case. It's really close. And we call that leptokurtic, right? If you were to calculate the stat, it would be called K, and K would be greater than 0. And so this curve is really skinny. So if we take the analysis that the Earth is 46 billion or trillion or whatever it is years old, and we were to try to plot the quantity of people, like the population of the Earth on that. Now let's imagine my x-axis starts from 0, whatever, find my, 0, whatever the beginning of the age of the Earth is. And then way over here, this is now, right? Imagine the scale, right? It'd be like nothing, 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 nothing. Now we're like 8 billion people, right? That would be leptokurtic because it would be like nothing, 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 tightly, compared to the age of the Earth. The period of time which our population exploded is really, really, really short. So it would be leptokurtic. No doubt. I have absolutely no doubt. Okay. Now, platykurtic is the opposite. It's like you took the curve and grabbed the sides and stretched it out. And what it means is it's just not well clustered around the mean, right? It means that there's a lot of data kind of spread out. And as you can imagine, standard deviation in B is tiny, and the standard deviation in C is huge. So platykurtic could be something like if I wanted to offer, I don't know, knitting classes to the community and everybody took me up on it. You'd have toddlers somehow knitting in the class, and you'd have, great-great-great-grandpa over here knitting in the class, and they would have really widespread in age. And that would be platykurtic. And if you were to calculate what we call a kurtosis stat, that is negative. It is less than 0, okay? So if you ever have a kurtosis stat and it's negative, it is platykurtic. It's spread out, okay? All right, so outliers. In terms of outliers, they're calculated in terms of distance from the mean, in terms of standard deviation. And again, remember, standard deviation is tiny if we got the skinny curve, and it's huge if we have the flat curve. But, the question is, do you calculate that before or after the outliers, so on and so forth. But if I were to ask you, are there outliers? What I'm really asking you is, are there people that are, or participants or data points, whatever, that are incredibly more far than you would imagine from the mean or the mode, okay? From the center of the distribution. It'd be kind of like, if for example, in the history of the Earth, if there was I don't know, if there was a time traveler, or 5 of them, let's say, that travel back to 70 billion years ago, or I don't even know, sometime halfway between here and the beginning of time and the Earth. Halfway in between, suddenly there'd be a blip, right? There'd be a little bloop, there's people here otherwise there were none. And so they would be outliers because the vast majority, billions of people, are so over here. It's very easy to get outliers actually with something tall and skinny. But anyway, the little blip, that'd be an outlier, right? It's just not what you expect. It's not representative of the curve, okay? So that's the purpose of identifying outliers, to go, hey, this might be a mistake in some way, and you have to go about it in a very systematic way. If you're curious on what that is, talk to me, but it's not important for right now. Okay, so which of the following scenarios are likely to have outliers, right? So number 1, a distribution is greatly negatively skewed. Again, rule of thumb should, rule of thumb should be up to the left, right? Hugely skewed, but not kurtotic, right? It's a nice curve, except for way out to the left. Is it likely to have outliers? Sure, because to be greatly skewed, it means there's somebody out here, right? Yeah. Distribution is platykurtic but not skewed. It means it's flat, right? I mean, it depends, but it's very possible that to be platykurtic, you could have the one where the distribution is nice and even, like I was talking about with the community, or you could have a normal curve with one outlier on each side, and that could also make it flat, like platykurtic, right? So number 1 and number 2 are very easily situations where you could have outliers. Now, you need more than just those stats to make a 100% decision, but it's very likely. Whereas if the distribution is normal, by definition, there are no outliers. That's what makes it normal. And then it's slightly positively skewed and leptokurtic. If it's slight, it's probably doesn't have outliers. It's just kind of a little bit shifted. Okay. Yeah. Okay. Notice that down here I talked about one-tailed or two-tailed outliers. The like where it like trails off on the side of the curve is called a tail, if you've forgotten that term. If you only expect it on one side, it's probably skewed because it's a one-tailed outlier. And if it's on both sides, it's a two-tailed outlier. Okay. I'm looking at my little camera to make sure my fingers are useful to the extent that they're ever useful, but it's fine. Okay. So moving on. P. P is a statistic. What is P? In inferential stats. And inferential stats are when we start calculating statistics in the sense of looking for group effects and so on and so forth. We're inferring things, right? P is generally is what we're using to decide if there are significant differences or not. So let's assume that the alpha level at P is significance is when P is 0.05 or lower, okay? There are a couple of ways to go about this. It's called an alpha level when you make that random choice, but the far and away most common one, short of some kinds of medical research, is 0.05, okay? So what is the 0.05? It's probability. P stands for probability, actually, if you were wondering, is what it means. And so P is the probability that the result of your test is due to chance. So when I say that it's 0.05, it's 5% or less likely to be due to chance. And that would make it significant, okay? This has to do with overlap and distributions. And this will make a little more sense when I show them to you in a second, but I want you to keep in mind, it means 5% likelihood or less, right? If P is less than 0.05, it's significant. We like that. We like it to be unlikely. And in fact, when the alpha level is different, when P is a different number, or significance is a different number, value of P, it's actually lower. Some medical research, P is significant only at 0.01. Okay. Now this is just a random cutoff point. 0.06 is not significant, and 0.78. So 0.06 and 0.78, both of them are not significant. It doesn't matter how close you are to that 5%. It is an arbitrary cutoff point, and you stick to it. Okay. All right, so when I say it has to do with overlap in distributions, what we're looking for is how much overlap. So if I am looking at two curves, they're called candidate A and candidate B for no particularly good reason. This is what they were called from the person who invented this. But the important part here is that there are two curves. These curves, let's just say they're normal, normally distributed, right? And so they have, a nice little mean there in the dotted line. It happens to be the same as the mode because it's a normal distribution. And they're different, right? The mean median of candidate or group A is down here at whatever 25% is, and the mean or median of candidate B, group B, whatever, is 27%. Now, here, you'll see these two curves have an overlap, right? There is a percentage of the values in which they are the same. Okay. This particular overlap, let's say it's 5%, as a person has said, but no more. So these two groups, A and B, are significantly different. So let's do it with an example. Two concerts at the same venue or on consecutive nights. Okay, let's say that concert A is whatever the hippest new band is, and concert B is an oldie but goodie band, right, that people have been listening to for 30 years. So you wonder if there's an age difference between the concert goers, because you would guess that concert A appeals to young people, and you would guess that concert B appeals to an older crowd. And if the two groups are significantly different, if I were to calculate that difference, what would that mean? So if I were to look at this curve, again, the left one would be so imagine the horizontal line here is age, right? And the left curve is concert A, and the right curve is concert B. Okay, not everyone who goes to each concert is the same age, so the curve represents the percent, the respective ages of the people who go to the concert, right? So let's imagine the mean and the median of the left one is 21, and the mean and median of the right one is 50, or something like that. There's still going to be spread, even though concert A, the mean is 21. There are some teenagers there, and there's some people, in their 30s. And on the right, the mean median might be 50, but there are people there in their 70s, and there are people there in their 30s. And you can see there is some overlap. I said in both cases there are people there in their 30s. And so what you want to know is that, do they overlap 5% or less? Okay. Because if they were to overlap 5% or less, they would be significantly different, okay? The populations would be significantly different, okay? So again, here it is written out in words. If the crew groups are significantly different, so if I calculate a statistic and get a p-value, it would mean the probability the age of the two groups is the same is less than or equal to 5%. Or that the two groups of concert goers overlap no more than 5% in age, okay? And just for the sake of this example, let's imagine that happened. It would look kind of like this with a handy dandy orange highlighting in the middle, okay? That's what P is. P is looking for overlap, percent overlap. And if it's 5% or less, these groups, we would call them different. And the idea is that sometimes the groups are similar, except for you've changed just one little thing, right? And you want to know, did that one little thing make a difference? So are your groups, as a result, different? Is there an effect of that one little thing? Like this could be test scores of people who slept 4 hours and people who slept 8 hours. And the people who slept 4 hours did worse on average. People who slept 8 hours, I don't know, I'm making this up. But the overlap is 5% or less, right? And if the overlap between people slept 4 hours, people slept 8 hours is greater than 5%, we'd say they perform the same. That is how that works. All right, so this has to do with group differences. The situation I just described with the concert or the groups of 4 hours and 8 hours, we would use a t-test to determine if they are different. So when do you use that? When you're comparing two groups of people or two sets of data, or sometimes you refer this as levels of a variable, right? So observations from two levels of a variable. So let's say, so imagine that the variable was hours slept, 4 hours slept or 8 hours slept, or the variable was concert A or concert B, okay? That's when you use a t-test, when there are two levels or two groups, okay? So if we think back to the non-human language, the NHL project data, mine were Wookiees, if you recall. What's a possible t-test? Well, one of the variables has two values, right? I think it's the group variable, right? I think that's B. We'll see it in a second, in a couple minutes down the line. On slide 19, you will see my example, and then you will know which variable it was. But anyway, mine were different colors of Wookiees. So I could use a t-test between group of Wookiees A and group of Wookiees B by, I don't know, I think it was curly fur and short fur or something like that, okay? So whatever your group variable was, you could run a t-test on that because there's two values, and thus two groups. Okay. Now in ANOVA, and to my knowledge, a percentage of the classes that do stats, certainly on our campus, I'm not sure where else, do not talk openly or specifically about ANOVAs. ANOVA means an analysis of variance. That's what it stands for. The T in t-test just means test. So it's a test. But anyway, ANOVA. An ANOVA is very similar to a t-test. In fact, they're conceptually the same, except for instead of two groups, you have three or more. Okay. So if I had 3 concerts, right, and concert C was whatever the newest kid thing, they would probably be younger when they went to that. So the question is, I could compare concert A, which is the hippest, newest thing, concert B, which is an oldie but a goodie, and concert C, which is for teeny tiny children, and look at the age group differences. I would use an ANOVA because now there are 3 groups, okay? That's truly the only difference between these, okay? If you really get down to brass tacks. So if I ask you what's a possible ANOVA from our NHL project data, if you recall our populations, there was a variable, I think it's column C, where they differed by location. In my data set, they're like treetops or something, I think. And those three locations, that's three groups or three levels of a variable. Ergo, I would use an ANOVA if I wanted to know about variable C. Okay? It may or may not have been planned that way when the data sets were made. Okay, so let me give you some examples and you tell me, t-test or ANOVA. Do 201 learners, and I mean like ASL 201 or French 201 or whatever, a language, learners outperform the 101 learners, again, ASL 101, French 101, whatever, on an interpretation task. How many groups? 2. T-test or ANOVA? T-test. Are French or Italian native L2 learners of English. So L1 Italian, L2 French. Sorry, L1 Italian or L1 French. Native L2 learners of English. So both groups are L2 English. Better on than monolingual speakers, monolingual children who speak English in a cross-modal priming task. Whew! That's a mouthful. Okay, so let's look in here. How many groups? I have my native Italians learning English, group 1. My native French learning English, group 2. Monolingual children who speak English, group 3. So what do I need? An ANOVA, because now I have 3. Okay. And then if I were to test, do English monolinguals rate A or B higher? Where are you? Where are you at? B is in my dialect. People have sometimes mocked me for that. Depends on what your dialect is, how you'll feel about it, but it's fine. This is 2 types of items. So it's the same people, but it's different items. So t-test, 2 levels, okay? All right. So what if we don't want differences? What if that's not what we were going for from the outset? So what kind of stats do we run if we want to look at relationships? Is like, are scores on a production task related to scores on a comprehension task? Now related, we're not talking about causing it. We just want to know if they co-occur, which means I'm looking for a correlation, right? So as one happens, the other happens at the same time. Correlation, co-occurrence. What if I want to say, is variation in proficiency score predicted by age of acquisition? Predicted, that sounds like causality, so I'm going to do a regression, right? And how are the above different? Correlations don't make claims about causality and thus are more sensitive, right? If I try to run a correlation, just looking for a co-occurrence of something, I don't need as strong of a relationship to get, let's say, significance or something, right? It's easy to get a correlation. It's hard to get a regression, right? And we talk about correlations a little bit more in this class with the with the spurious correlations website/book. And if I haven't talked about it, remind me because we should talk about it. Okay, so here, now we're on slide 13. Now slide 13 begins the section on repetition. We're getting into the more complex pieces. This does not relate so specifically to the NHL project, but it could very much relate potentially to the study that you're replicating. Okay, so what's happened up to here is extremely important. What from here until when I tell you is moderately important. Okay, so repetition. I want you to imagine 2 data sets. Okay, in the first, there are 2 columns representing scores on a French test and a German test, respectively. Okay. So it's just a data set, right? You're just imagining 2 columns, they have scores in each one. Each test has a measurement for 10 people, but no one who took the French test took the German test and vice versa, okay? So essentially, how many people do I have in there? 20. So French 1, French 2, French 3, blah, 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 French 10. And then different group of people, German 1, German 2, German 3, 10, okay? 20 people, so 10 in each column. Compare that to this one. There are 2 columns representing scores on an ASL test administered in ASL 201 and ASL 401 respectively. Imagine, okay? Each row, however, represents 1 student who took the test twice, once in ASL 201 and once in ASL 401. Same people, okay? These are different, right? How many participants are in this? Imagine that in both cases, there's only 10 rows. In the first experiment, there are 10 rows and it's 10 people and 10 people. In the second data set, there are 10 rows, but each row is one person. So now there's only 10 people, okay? I've essentially repeated a test on the same people within a row, right? So these data sets involve, the first one is what we call independent, and the second one is repeated, also called paired if you're talking in terms of t-test, but it's a repeated, right? It's the same person, essentially, doing it twice. There are ways to make this not people too, but for the sake of what we're doing in this class for linguistics, it's pretty much always people. Okay, the same person gave you judgments or scores on a test across the board, okay? So variables will differ in regards to whether they assume observations are related or not, right? So if they're unrelated, such as belonging to separate people in case of a French and German test, they are independent, as I've said. And if they are related, like belonging to the same people, they are repeated or related or paired sometimes, as I've said. And this question is sort of, I've kind of given the answer, but if I were to ask you to run an independent t-test, a repeated t-test, or a paired t-test, because repeated and paired are the same, on the previous two scenarios, first of all, the answer is independent when they're different people and paired or repeated when they're the same. What does that mean for you? That just means making sure that when you run the test, your model knows which one it is, because the math makes a different assumption when it's the same people than it does if they're different people. And in fact, the one that's repeated is a little more sensitive, as a matter of fact, because it's looking for differences within a person, whereas the other one is looking, it realizes there's going to be some differences between groups because of the fact they're different people. Inherently, there should be more variance in independent t-test, so it's not as sensitive, whereas a repeated t-test or paired t-test is more sensitive because it's assuming it's the same person in each row, so it's looking for change as opposed to kind of overall change, right? So, but again, what your job would be if you were to do one or the other, because you will do one of these for a lab, is you just tell it which one, right? And I think in our case, it's independent. I'm pretty sure, but I'd have to look, okay? So you just tell it which one it is and it will spit it out, but you have to make the correct choice because it will change assumptions, it'll change the math, and it will change how sensitive it is. And sometimes it's inappropriate to use one or the other. ANOVAs have the same possibility, right? Again, ANOVAs and t-tests differ truly only in that t-tests can only be 2 levels and ANOVAs are 3 or more. Actually, if you run a so-called ANOVA on 2 groups as opposed to 3, it's the same exact output as a t-test because that's what they are under the hood. Now, I said paired t-tests are a simple example repetition, but ANOVAs can be repeated, such as, well, if I ask you here, if we were in class, I would say, what's an example? It'd be something like this. Imagine I did, I don't know, a lot of my examples are from L2, obviously, but imagine I did an experimental design with a pretest, an immediate post-test, and a delayed post-test. So I take a group of, I don't know, learners of Chinese, and I assume they don't know the classifier system very well. I give them a pretest, seeing if they can use it. Then I teach them something about it, and I do an immediate post-test. And then 6 months later, come back and I test them again on the same items to see if they retain that knowledge. This is a pre-test, post-test design, often with a delayed post-test involved. Okay, that's 1, 2, 3 with the same people in every row, right? I have a column for pretest, a column for post-test, and a column for delayed post-test. And even if I only have 10 rows, those are the same people in the row, right? It's person 1 does a pretest and a post-test and delayed post-test. Person 2 does a pretest and a post-test, delayed post-test, etc., 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 okay? This is repetition in ANOVA. And once again, it is more sensitive because the model knows it's the same person. So here's another example, monolingual judgments on 3 related items. So if I gave a person a whole big thing and I said, okay, good or bad, all these sentences, and embedded in there were a set of sentences like A and a set of sentences like B and a set of sentences like C. John believes Sue to be intelligent. John believes Sue to have run a mile. John believes Sue to have run a mile. Better, maybe not as good as A, whatever. But imagine that I gave a group of monolingual English speakers these three sentences, and I then wanted to see if they felt the same about the three of them. If I had a column for A and a column B and a column for C, I would have a row for each person. Once again, person one likes A better than B and C, and B is the worst, and C is somewhere in the middle. Ditto, 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 which is exactly what happens if you do this on monolinguals. I would know because I've done it. And so this would also be a repeated ANOVA, right? You want each person's judgment on three different categories, three levels of the variable, okay? All right, so more complex designs. Okay, so this is where stuff that kind of goes a bit beyond this class can start. Okay, if you're following me so far, I invite you to totally jump in with 2 feet. But if you're not following me so far, maybe pause and come back to it later, especially if it so happens that something like this appears in your article. And that's actually very possible, as a matter of fact. When I say more complex designs, it's only more complex from a statistical point of view. It's super common. Okay, so this is not like way out there stuff, but it is, but it's more complex than we've done so far. So some models do have more than one independent variable, okay? And these examples are with ANOVAs. And one thing I'll say is that, I'll come back to it, okay. So imagine a 2x2 ANOVA, okay? And you're like, oh, hang on a second. First of all, I see 2s. I think you told me ANOVAs had 3 levels. Bear with me, okay? Now this ANOVA has 2 independent variables and both have 2 levels / groups, okay? So imagine I had a judgment task with the variables type and language, ASL and English. So I wanted to know how imagine that there's a group of people learning ASL and a group of people learning English, or maybe monolinguals of these languages. Let's say monolinguals these language, right? So some native signers, monolingual ASL users, and then English monolinguals who've never learned anything. And then I give half of those ASL signers items with questions in them, and and then the other half gets statements, right? I want to say, are these good or these bad, and whatever. And then in English, we do the same thing. Notice that I proposed only giving giving the question items to half of the ASL users and not like mixing it, because that makes repetition. But anyway, 2 variables, type and language, okay? This is a 2x2 ANOVA would be the most appropriate way to analyze this. And you're going to say to me, Jeannie, you told me that you had to have 3 levels to run an ANOVA. Yes, unless it has more than one variable. And in fact, once you have 2 variables or more, it's never a t-test. T-test is always 1. T-test is the simplest by far. ANOVAs are very versatile. They have some drawbacks, but they're very versatile. You could have 4 variables, 6 variables, if you really wanted to. You could do that. But that's what you do. So as soon as you have 2 variables, it's called an ANOVA again. Why? Because it isn't a t-test. That's the only real answer. But ANOVA is basically group differences, kind of in a general sense. So it can be group differences with 2 variables, group differences, 1 variable with more than 3 levels, 3 or more levels, or it could be 4 variables, okay? A 3x2 ANOVA. Okay, let's look at my previous example. Type has 2 levels, language has 2 levels. All right, 3x2 ANOVA. One of those variables has to have 3 levels now. So 2 independent variables, one with 2 levels / groups and one with 3. So a judgment task with the variables question and statement, except for now I've got 3 languages, ASL, English, and Libras. And Libras is a signed language in Brazil, excuse me. Okay, yeah? So now I have 3 levels. So if in your study that you are reading, you see these little number by number ANOVA thing going on, it's because they're trying to tell you how many variables they have and how many levels there are in those variables. And if you were to be writing these things and doing fancy ANOVAs, which you won't do those for me, this is how you would report it. Okay. Oh, now we have a 2x2 ANOVA. What would that mean? Has 3 independent variables, and all of them have 2 levels or group. Now notice the number of numbers indicates how many variables, and the quantity in each of those tells you how many levels. So 2 by 2 by 2 is 3 variables, each have 2 levels. So if I had a judgment task with the variable type, 2 levels, language, ASL English, and subject, pronoun or full DP, that would be a 2 by 2 by 2 ANOVA. Except for, yeah. So that would be so that's 3 levels, 3 variables, 2 levels each. And then I get a repeated measures ANOVA. Now remember, I said you could have repetition. So let's imagine instead of me saying half the ASL people saw questions and half the ASL people saw statements. Let's imagine that now they're seeing all of them. It's the same person in both columns. So 2 independent variables, both of which have 2 levels or groups, and at least one of them has a repeated value. Okay, so just because we've been talking about pre-tests and post-tests with repetition, this would be a way to do that, right? A judgment task with the group, let's say even L1 and L2, and test, pre-test versus post-test, right? So there's 2 levels, 2 groups, sorry, two variables, each of which has 2 levels, which could be a group or just a, value like pre-test, post-test. And one of them at least is repeated. And in this case, group is repeated, right? The same row is the same group, okay, right? The people in the L1 group are going to see pretest and post-test. People in the L2 group are going to see pretest and post-tests, okay? So this is what we mean. This is about complexity, okay? So some vocabulary when we talk about repeated measures. If people were to be writing, if you were trying to read and understand what was happening, the words within and between are very important because they tell you which one is the repeated variable or if both are. So if I said a judgment task with the variables group and test, right? I would have to write it up kind of like this for the judgment task. A 2 by 2 repeated measures ANOVA was run with the between subjects variable group and the within subjects variable test. The dependent variable rating probably. So when I say between subjects variable, I'm saying that one's not repeated, right? So there's group and they don't overlap. When I say the within subject variable test, that's the one that's repeated because everyone in each group does both, right? That the row is shared essentially. There's a value for participant number 1 who happens to be in group 1 for pretest and post-test, okay? So when you see those words, that's what they're trying to say. Between means I'm not repeated. Within means I am repeated. Okay. All right. So what ANOVA could I do with multiple variables based upon our data set? So here's my my groups and my treetops. For wrench juggling and complementizer per sentence. Okay, let's just stick to wrench juggling for the moment, right? This is the rate with which each participant juggled wrenches per week or something, right? 98 times per week. I don't even know. But whatever, it's fine. So, okay, we've already said the group has 2 levels, right? Because we said that if you were just looking at the effective group, a t-test would be sufficient. Right? I could do the average for curly fur and the average for short fur and be done with it. And it would be independent. Treetops, if you recall, we said has 3 levels. In this case, I have these somewhat illegible Kachiro and Thikiana. I don't even know. Something like that, right? 3 levels, we said. Because we all have three levels in our location variable, which is column C. And we said that has to be an ANOVA because there's 3 levels. And if I wanted to look at these affecting wrench juggling, then, I would either run, if I want to know just the group, then I would do wrench juggling. If I want to know just the treetops, I would do an ANOVA. I could also do the multivariate ANOVA that we were talking about, right? So in this case, we would get, this would be a 2 by 3 ANOVA. The order is not important, right? 2 for group and 3 for treetops, a 2 by 3 ANOVA. Which brings up a question, why would I do that? Why not just run a t-test and then an ANOVA separately? So here's the thing, when you run a multivariate ANOVA, they give you something called an interaction. And I can't recall if this shows up later. No, not yet. An interaction, which tells you what is the significance of the relationship between them. So let's imagine that all of these people juggled a heck ton of wrenches, except for short-furred Wookiees from Thikiana just happen to hate wrench juggling. there would be an interaction in that data set that would say, actually, these are all the same except this one subgroup, right? That's what doing a multivariate, a 3x2 or something, allows you to do, is to go, hey, actually, there's one little tiny combination of the variables, something different happens. That's the importance of doing multivariate if it's available to you. Because if I do A and then B, if I did, a t-test on B and a ANOVA on column C, I would lose that information, okay? So anyway, this is just for you to understand what you're looking at, not to run these things, okay? And watch it a couple times. It may not stick the first time. It depends on your previous experience with this stuff. All right, okay, so this stuff here is extra innings, okay? There's a small chance that one or two of you will have regressions in your data set as opposed to ANOVAs, and that's fine. Some of you won't even have ANOVAs, right? It's fine. So let's imagine, for the sake of argument, that a regression can be more complex. A regression, remember, has to do with, it's like a correlation in which you have two linear variables. Do they co-occur? Except for regression is trying to make claims about one causing the other. So a linear regression is a regression with one independent variable, continuous variable, and one dependent continuous variable. So an example of where you could do a correlation and a regression, because you can do them in basically the same data sets, except for one's causality, one's not, would be, let's imagine that if I had number of hours of sleep before a test and score on that test. Let's imagine I had that that data set, right? And I said that they were correlated. That would say that the more hours of sleep, the better I did, although probably at a certain point it doesn't help anymore, but Okay, so that would be a linear, right? So, or my example from this particular presentation is age of acquisition and proficiency probably have a negative relationship, which is to say that if you learn a language younger, you might be better at it in the end. I don't know, depends. Or something can be multilinear, right? Multilinear, in the same sense as suddenly we have more variables in these multivariate ANOVAs, you can have more than one independent variable, okay? It could be the case that more than one thing is predicting the other thing, okay? And typically only has one continuous variable. I haven't gotten into the issue of multiple dependent variables because it can happen, right? We have two output variables in our data set, D and E, and there are ways to involve both of them in the same model, but I wouldn't do that to you. Okay, it's not necessarily important to do. Sometimes you don't even, interpreting it, you'd really have to need to do it that way. Anyway, let's imagine I did instead, so now I have, again, three continuous variables because regressions and correlations require continuous variables. The relationship between age of acquisition, age at time of testing, and proficiency. So let's imagine age at time of testing, the ages of like 2, 3, 4, 5, 13, 14, 15, 16, maybe there's stuff in the middle, and age of acquisitions in there, and then the proficiency. I would be looking at whether age of acquisition and age of time of testing predict, that's why it's a regression, predict proficiency. Okay? It's very possible. There's also a small chance that you may see some version of mixed models. And mixed models are basically, they're basically the things we've already looked at with slightly different assumptions. So if you find yourself looking at any form of so-called mixed models, and this can be linear mixed model, general linear mixed model, et cetera, et cetera, et cetera, it functions like a cousin of one of the existing models, except for that you can specify whether an effect is fixed or random, right? So for example, there are people that for various reasons will include the item, right? Imagine I did a judgment task on 100 items, and then it has two types of items and two groups or something. Some people want to include the item itself as a random variable, right? It's not really planned to cause variance, but it could. Whereas the groups that you planned, or the item types that you planned, are what they call fixed variables, right? And this is it. Fixed variable or effector planned and measured like sentence type, and random is unplanned like participant, actually. Sometimes they use participant and item number are the most common random variables in linguistic studies, I would say. There potentially are others, but they're the most common because you don't know who you're going to recruit. You don't know whether this random item is weird for some reason. And so you can do it this way. The other way is look for outliers and yank them, but that's a different thing. anyway, if this applies to you, if for the sake of argument, someone has some kind of mixed model in their study, you should be focusing on what variables are relevant to the research question, right? Such as if you happen to have a GLMM and you are looking for, again, the effect of age of acquisition on proficiency, but there's a bunch of stuff all smushed up in there. You are looking for the variables in your research question. And you say, okay, and the effect of age of acquisition was this, right? All that other stuff for this class, I wouldn't worry too much about. There are reasons to interpret it, and you would probably need to come and chat with me about the specifics of what those models mean. But it's not as bad as it sounds. I'm basically going to boil it back in terms of something vaguely ANOVA-ish, because again, they have a heck ton in common with these, right? The difference again with a regression is just whether it's prediction or not. ANOVA is looking for group differences. Regressions are looking for prediction. Otherwise, they're very similar. And it has to do with what kind of variables are under the hood. In fact, some of these things involve binary variables. Some of the mixed models are actually binary, and that's why they can't be ANOVAs or something, because the assumptions are different. They're binary. All right. There are some fancy regressions too. Oh, this is like the binary thing, where the output variable isn't continuous. So imagine that now I want to know whether I can predict the outcome on a binary variable. So whether all these other variables can predict whether a door is open or shut, binary, right? I want to talk about predicting variance in some way. Then there are some other fancy things, right? The binary logistic regression, so such as a judgment task with the independent variables, whatever you want, and the dependent variables, yes or no, right? That's another binary variable that you could stick into these guys. And once again, I can boil this down in very simple terms, but it would depend on the exact example. The general ideas are still the same as the ANOVAs or the regressions, right? That you are either looking for group differences or trying to predict an outcome. It's either significant or it isn't, okay? All right, heck ton of this. We will talk about, as I said, kind of the first half of this stuff in class, and kind of talk it through and work with it a tiny bit more. But the rest of this, if you have questions on it, shoot me an email. I am happy to talk to you. We could even Zoom about it, whatever. Talk to you in more detail about this, okay?